Welcome to day 96, and obviously you wouldn't have been able to see this integral from the thumbnail because I covered it up, but I do think it's a very satisfying definite integral, so stick around for the solution and of course try it yourself first. So the first thing that I notice when I see this integral is this ln of x, and I know that the derivative of ln of x is 1 over x, and this is just like screaming at me because I see these x's here that I can take out as a common factor, and then I can do a neat u substitution for ln of x. So I'm going to go ahead and do that, and I'm going to say let ln of x equal to u, and then du is equal to 1 over x dx. And then of course with a definite integral, when we're changing our variable, we've also got to change our limits of integration. So we're integrating x from e to infinity. So then when we integrate u, we substitute an e in here, and we notice that ln of e is simply 1. So we integrate from 1, and then we substitute in infinity into ln of x, and ln of infinity also is infinity. So we have u being integrated now from 1 to infinity. So now we are integrating from 1 to infinity, and now just notice for this denominator quickly, I'll just write it in here. This is also equal to x into 1 plus ln of x squared. And that's what I was saying earlier with this ln of x and this 1 over x as the derivative of ln of x coming out very nicely, because that's a denominator. Alright, so we substitute in for ln of x, we're going to substitute in u. So we have u squared, and then this x came out, and then what we would have here is an x and a dx, but we're substituting in du for 1 over x dx. So that actually goes, and we write du. And then we of course know that this is, the integral of this is simply arctan of u. So now we go ahead and we say arctan of u from 1 to infinity. And actually something that I should have done over here, and I'll do it quickly, is should have said the limit as t approaches infinity and made this integral from 1 to t, 1 over 1 plus u squared du. And the reason why this is important is because you can't necessarily substitute in infinity over here later on when you're going to have arctan of infinity minus arctan of 1. You can't necessarily do that. And the reason why is because infinity is not really a number. So you can't substitute in infinity because you can never be at infinity. Infinity is a concept. You can only approach it. So instead we're going to substitute in this t, and we're going to approach, and we're going to make t approach infinity through this limit. So that's like essentially how limits work, and it's a nice way to get around this idea of not being able to substitute in infinity directly. So we put actually a t over there, and then we say the limit as t approaches infinity, and then we can say the limit as t approaches infinity of arctan t minus arctan of 1. And I remember a good way to think about it is to draw your tan function, which looks like that, and it has this asymptote as pi by 2, and now your tan is equal to 1 at pi by 4, which is 45 degrees. So, or pi by 4 radians. So, if this is our tan function that I've just rubbed out, then our arctan function looks like that. Okay? So then, tan is equal to 1 at x equal to pi by 4. So for arctan 1, we can substitute in minus pi by 4. And as t approaches infinity, so as we move along there, arctan approaches pi by 2. So we have pi by 2 minus pi by 4, and that simply leaves us with pi by 4. So it worked out to a very nice number as well, which is also part of the reason why I found this integral so satisfying. I hope you also found it satisfying, and I'll see you guys tomorrow for day 95.